Welcome to this deep dive. Today, we're plunging into a really fundamental problem in computer science, something you probably run into more than you realize, the edit distance problem.
That's right, often called Levenshtein distance, too.
Exactly, Levenshtein distance.
And at its core, it's a way to measure how alike two sequences are, usually strings. We're trying to find the smallest number of changes needed to morph one string into the other.
Right, and we're only allowed 3 specific kinds of changes, yeah. According to the source material, it's inserting a character, deleting a character,
Yeah.
or just replacing one character with another one.
And the classic examples really help clarify it, I think, like changing kitten into sitting.
Ah, yeah, kitten to sitting.
You swap K for S, E for I, and then you stick a G on the end. That's 3 edits.
3 edits, okay.
Or another one is hello to algo.
Hello to algo. Let's see, A to A, E to L, and then you have to drop the last O.
Exactly. 2 replacements, 1 deletion, also 3 edits. It shows you immediately it's not always obvious what the minimum path is.
Which is really our mission here, right? We want to go beyond just seeing those answers. We want to help you really get, and hopefully remember for good, how we can systematically find that minimum number.
We're going to walk through this really powerful technique called dynamic programming, kind of step by step.
Yeah, break it down so it clicks, so you really grasp the logic, not just hear it. Okay, so thinking about that, finding the minimum number of edits. If you just start trying things, insert here, delete there, replace this, it feels like you could go in circles forever.
Yeah.
How do you find the best path?
That's a good way to put it. The source material actually suggests thinking about it first like a decision tree.
A decision tree.
Yeah, imagine your starting string, say hello is the root, then every possible single edit you can make, inserting something, deleting something, replacing something, is like a branch leading to a new string.
Okay, so from hello, I could branch to LO by deleting H, or hello by inserting A, or maybe jello by replacing H with J. Wow, yeah, that branches out fast.
Insanely fast. And each of those new strings becomes a node where you can branch again. In this model, the target string, like algo, is somewhere down in that massive tree.
So the problem becomes finding the shortest path from the hello node to the algo node.
Exactly. That's the conceptual model. The number of steps on the shortest path is the edit distance.
But like you said, that tree gets huge. Building it out and searching it, that just sounds computationally nightmarish for anything but tiny strings.
It really is. Completely intractable. You'd explore billions of paths. So while the tree helps visualize the possibilities, it's not how we actually solve it efficiently.
So what's the smarter way?
We need a technique that's good at finding optimal paths when you have lots of overlapping work, where you'd end up solving the same smaller problems over and over in that tree, and that's where dynamic programming comes in.
DP.
Yeah, DP is perfect for this. It works by breaking the main problem, transforming string S to string T into smaller, overlapping subproblems. You solve each unique subproblem just once, save its answer, and then reuse that answer whenever you encounter that same subproblem again.
Okay, makes sense in principle. But what are those smaller subproblems for edit distance? How do we define them?
This is the elegant part. The subproblem is defined by prefixes. We ask, what's the minimum edit distance between the first I characters of string S and the first J characters of string T?
Prefixes, right. So not just random chunks, but the beginnings. Like if we're doing hello to algo, a subproblem might be finding the distance between hell and al.
Precisely. We usually denote the answer to this subproblem as d pi ij. That d pi j represents the minimum edits needed to change S up to index I into T up to index J.
Okay, d pi I. You mentioned saving the answers. How does that work?
Well, this d pi ij structure naturally suggests using a grid, a two-dimensional table. If S has length n and T has length m, we use a table of size m plus 1, xm plus 1.
Plus 1. Y plus 1.
Good question. It's to handle the empty string case easily. Row 0 represents transforming the empty prefix of S, and column 0 represents transforming to the empty prefix of T. So cell ij in this grid will hold the answer for Si and Tj.
Got it. So we fill this grid, and the final entry, the distance between the full strings will be in the bottom right cell, dpnm.
Exactly. The whole game is figuring out how to fill each cell dpi. J using the values in cells we've already filled, representing smaller subproblems. This is the state transition.
And how do we figure that out?
We look at the last characters involved in the current subproblem, psi1 and tj1. Remember, strings are usually 0 indexed, but our DP table is 1 index, so psi1 is the ith character.
Okay, the characters at the ends of the current prefixes.
Right. There are 2 main cases based on these characters.
What's the easy case?
Easy case. They match. Psi1 is the same as TJ1. If the last characters are already identical, well, we don't need an edit for them.
Nice, so no cost for that step.
Correct. The cost to transform SI to TJ is just whatever it costs to transform the prefixes before these matching characters, which is SI1 to TJ1.
And we already calculated that.
We should have if we fill the table in the right order. That cost is stored in dpi1, J1. So if psi1 then dpi_j is simply equal to dpi1, J1.
Okay, that's clean. Inherit the cost from the diagonal upper left cell. But what if they don't match? Psi1 is different for TJ1.
Right, that's case 2, the more involved one. If they're different, we must perform one edit operation involving these characters to make progress. The question is, which operation leads to the minimum overall cost? We have 3 choices for the last operation that could get us to the state dpi_j.
The insert, delete, replace options.
Exactly. Let's think about them. Option 1. Maybe the last operation was an insertion. We could have transformed SI into TJ1. The cost for this is dpi_j1, and then inserted the character TJ1 at the end. That insertion costs 1 edit. So the total cost via this path is dpi j-1 plus 1.
Okay, transform S up to I into T up to J1, then pay 1 to insert the last character of T. Makes sense.
Option 2. Maybe the last operation was a deletion. We could have transformed SI1 into TJ, cost.dpi1j, and then deleted the character psi1. That deletion costs 1 edit. Total cost, dpi1j plus 1.
Right. Transform the shorter S prefix into the current T prefix, then pay 1 to delete the last character of S. Got it.
Option 3. Maybe the last operation was a replacement. We could have transformed SI1 into TJ1, cost dpi1, J1, and then replaced psi1 with TJ1. That replacement costs 1 edit. dpi1, J1 plus 1.
Okay, transform the shorter prefixes, then pay 1 to replace the last character of S with the last character of T.
So if the characters psi1 and TJ1 don't match, we have these 3 possible costs based on the results of smaller subproblems we've already solved or will solve before we get here, since we want the minimum edit distance.
You just take the minimum of those 3 possibilities.
Exactly. dpi_j will be the minimum of dpi_j1 plus 1, dpi1j plus 1, and dpi1j1 plus 1. Or you can write that as mine dpi_j1, dpi1j, dpi1j1 plus 1.
Okay, that covers the logic for filling any cell based on its neighbors left, above, and upper left. But how do we start? Where does the very first value come from?
Good point. We need the boundary conditions, the base cases, to get the whole process started. Think about the cell dp0, 0. That represents transforming an empty string, prefix of length 0, into another empty string. How many edits?
0, obviously.
Right, so dp0, 0, 0, 0, 0. That's our anchor. Now, what about the first column, dpi0 for I0? This is transforming the first I characters of S into an empty string.
You just had to delete all I characters of I edit.
Exactly, so dp0, 0j, that fills a whole first column. 0, 1, 2, 3, down 10.
And similarly for the first row, dp0, j, transforming an empty string into the first j characters of T.
You'd have to insert all j characters.
So dp0j equal j. That fills the first row, 0, 1, 2, 3, across to m.
Perfect. Those are our boundary conditions. They seed the grid. Now we know how to calculate any other cell dpi_j based on values that are above it, to its left, or diagonally upper left.
Which implies an order, right? We have to calculate those neighbors before we calculate dpi_j.
Absolutely. The dependencies dictate the order. Since dpi_j needs values from row I1 and column J1, the standard way is to fill the table row by row, starting from row 1, since row 0 is a base case, and within each row, go column by column, starting from column 1, since column 0 is also a base case.
So like nested loops. Outer loop for rows I from 1 to n, inner loop for columns j from 1 to m.
That's the typical implementation. The source mentions it's kind of like filling the grid for the knapsack problem DP, if you're familiar with that.
Okay, so summarizing the process. Create the n plus 1x, m plus 1 grid, fill the first row with 0 to m, fill the first column with 0 to n, then loop I from 1 to n, loop j from 1 to m. Inside, check if psi1 equals tj1. If yes, dpi1j1.
Correct.
If no, dpi_j1n, dpi_j1, dpi1j, dpi1j1 plus 1.
That's it.
And after all the loops finish, the answer is sitting in dpm.
Precisely. That bottom right cell holds the minimum edit distance for the original strings.
That seems very methodical, very clear. But what about memory? If n and m are large, say thousands or millions like in bioinformatics, that n plus 1x, n plus 1 table gets pretty big, doesn't it?
It absolutely does. That O and M space complexity can be a real problem for large inputs. It's a very valid concern.
Is there a way around it? Can we optimize the space?
Yes, thankfully. If you look again at the calculation for dpi_j, notice which other cells it actually depends on.
Let's see. If characters match, just dpi1, j1.
Yeah.
If they don't match, it's dpi_j1, dpi_1j, and dpi_1j1.
Right. Notice they all come from either the previous row I1 or the current row I, but an earlier column, J1. You never need values from row I2 or earlier to calculate row I.
So maybe we only need to keep like 2 rows in memory at a time. The one we just finished calculating, row I1, and the one we're currently calculating, row I.
Exactly. That's a standard optimization. Instead of the whole m+1x, m+1 grid, you can use just 2 rows of size, m+1. When you calculate row I, you read from the stored row I1 and write into the space for row I. Then for row I+1, the row you just wrote becomes the previous row. This brings space down to OM. Assuming m is the smaller dimension, you'd orient the grid that way.
Okay, OM space is way better than ONM. Can we do even better, or is that the limit?
Well, you can actually optimize it down to using just 1 row of size m+1, plus a couple of temporary variables, so still OM space, but slightly leaner.
1 row. How does that work? If you overwrite the previous row's values while calculating the current row, how do you still access things like dpi_1j and dpi_1j1?
That's the clever bit, and it can be a little tricky to wrap your head around without drawing it. Let's call our single array dp of size m+1. When we are calculating the values for row I, this dp array will hold the values for row A. Now imagine we're about to calculate the new value for dpj, which corresponds to dp_j in the full grid. We need 3 values from the previous state: dpi, j1 left, dp1, j above, and dp1, j1 upper left. Where are they in our single dp array? dpi, j1 left is easy. That's the value we just calculated and stored in dpj1 in the current pass through the inner loop.
Right, we just computed that one step earlier in the j loop.
dp1j above is the value that's currently sitting in dpj before we overwrite it with the new value for row I. It's the result from the previous row's calculation for that same column j.
Okay, so we need to save that old dpj value before we calculate the new one.
Precisely. We store it in a temporary variable. Let's call it temp. Now the tricky one. dpy1, j1, upper left. Where did that value go? When we were calculating dpj1 just now, the value that was in dpj1 was dpy1, j1.
So the above value for the previous column, j1, was the upper left value for the current column.
Yes. So we need another variable to keep track of that diagonal value as we slide across the columns. Let's call this left up. Before we calculate the new dpj, left up should hold the value of dpy1, j1.
Okay, this is getting intricate. So for each cell ij, we need dpj1 from the current update pass, temp, holding the old dpj from the previous row, and left up, holding the old dpj1 from the previous row.
You've got it. Here's how the inner loop for j from 1 to m works for a given row I using just the dp array temp and left up. First, before the j loop even starts, we need to handle the boundary j0. The value dp0 from the previous row, I1, was I1. This value is needed as the initial left up for calculating dp1, i.e. dpr1. So we store the current dp0, which is I1, into left up. Then we update dp0 for the current row I, setting dp0i.
Okay, initialize left up with the old dp0, then set the new dp0.
Now inside the loop for j from 1 to m1, store the current dpj, which is dpr1, j, the above value, into temp.
Save the above value. Okay.
2. Calculate the new dpj, which will be dpy_j. Check if psi1 equals tj1. If they match, the new dpj is just left up, which holds dpi1, j1. If they don't match, the new dpj is mine, dpj1 left, temp above, left up, upper left, plus 1.
Calculate the new value using dpj1, temp, and left up.
3. Now, before moving to the next j, we need to update left up so it's ready for the next iteration. The value that will be the upper left for column j plus 1 is the value dpi1j, which we conveniently saved in temp. So we set left up, temp.
Wow, okay. Temp holds the above value for the current calculation and then becomes the upper left up further the next step. It's quite a shuffle.
It is. It's a clever way to manage the dependencies using minimal extra storage. The source notes this pattern is similar to the space optimization for the unbounded knapsack problem, if you've seen that. It feels a bit like magic until you trace it carefully.
Yeah, I'd probably need to draw that out, but the concept is clear. You can get down to just 1 row of space.
And after you finish the outer loop, all rows I, the final answer, dpn, m, will be in dpm.
Okay, fantastic. Let's just quickly recap the journey then. We started with edit distance. Minimum inserts, deletes, replaces between 2 strings.
Saw the decision tree idea helped visualize, but was computationally hopeless.
Which led us straight to dynamic programming, defining the state dpij for prefixes.
Figuring out the transitions. Easy if characters match. Take the min of 3 options plus 1 if they don't.
Setting up the boundary conditions for empty strings.
And understanding the row-by-row, column-by-column filling order based on dependencies.
And finally, we looked at how to optimize the space from the full O&M grid down to potentially just OM using 1 or 2 rows and some careful variable tracking.
Right. And the key takeaway is that DP table, however you implement it, systematically finds the optimal solution by building on optimal solutions to all the smaller, necessary subproblems. It's not magic, just structured calculation.
So for you listening, why did we dive so deep into this? Why should you care about edit distance? Well, as the source mentioned, it's everywhere.
Absolutely. Information retrieval is a big one. Search engines use concepts like this to find documents that are similar to your query, not just exact matches.
Spell checkers. That's a classic example, suggesting sitting when you type kitten.
Definitely. It calculates the distance to dictionary words, and bioinformatics relies heavily on it for comparing DNA or protein sequences. Even version control systems, when they show you differences between files, similar ideas are at play.
Basically, anytime you need to quantify how far apart 2 sequences are.
It's a really fundamental tool in the computing toolkit.
It is indeed. Well, that wraps up our deep dive into edit distance in the dynamic programming solution.
Hopefully that breakdown helps it stick.
And here's a final thought for you to chew on, kind of leaping back to that comment about the knapsack problem DP table looking similar. The source pointed out that visual similarity. Can you think of other problems, maybe ones you work on or have studied, where the best solution to a big problem seems like it's built by combining the best solutions to smaller, overlapping versions of itself?
Recognizing that underlying structure, that optimal substructure and overlapping subproblems is often the biggest clue that dynamic programming might be the way to go. Something to keep an eye out for.